Okay, so we continue the next part. The question, what is so special about acyclic queries? And we start discussing a powerful tool that gets rediscovered a couple of years. It's a very powerful idea that helps us speed up inference, query evaluations, and sometimes quite drastically. It is a semi-join reduction, and it is best known in the context of distributed databases. Assume you would like to perform a join between two tables that reside on two different machines, R and S. One possible way to achieve this is to send all the information from R to the other machine where resides S, perform the join, and then output all the tuples. An alternative is we could sometimes speed this up quite drastically if we only knew which of the tuples from R are actually relevant. Which one will join with S? If you could somehow reduce R. And the idea is here, if we send a message first from S to R, the message that contains all of the relevant B values, then we can first filter out here the R, we can reduce R to only those tuples that will join later on, and then send only those reduced tuples to S before we perform the join. And if the arity of B is substantially smaller than S, or if A, C are very large attributes, and if ultimately not all of the tuples from R participate in the join, then this can give quite a drastic speed up. Nikos has already shown before, I think, this example. Let's look at this again. You can actually play with this. You can go to this website, download a file, 601, and run it on your Postgres SQL instance to verify the numbers that we're gonna see here. So this is a parameterized database instance. You have about n tuples in R, 2n in S, and n in T. And the idea, the way it is created is, here we have a quadratic join between tuples R and S, here quadratic between S and T, but there's only one single join that survives the two joins, so there's only one single output tuple. So if we now run this query on a database instance that's increased from 1000 to 2000, then the time it takes to perform it takes four times as much. So it scales quadratically. If we, however, modify the query slightly to force the database to perform the semi-join reduction, then it scales only linearly, and we go from 6 seconds down to 8 milliseconds. So this concept that we have here, in a more abstract sense, is also called sideways information passing. So here's the idea. This is the join we saw before. In any sequence, we want to perform this join first, also by a table at a time, R with S and then T. Yeah, we join R with S. The intermediate size will be quadratic, even though the ultimate result will be only 1. And the only way we can avoid this quadratic intermediate result is by somehow perform some information passing between the tables. So sending information from one sub-expression, not simply to its parent expression, but also to some other correlated portion of the query computation in order to prune irrelevant results. And the semi-join is the most well-known example for this. Magic sets for data optimization is another one. So, acyclic queries, hypergraphs, and join trees. Let's look at hypergraphs first. So here's a conjunctive query in Datalog notation. The concept we often use is that of a hypergraph. So for the hypergraph, we take all of those variables, make them into nodes, and then the individual atoms are those edges, hyper edges. In this case, for example, R contains X and V. R, the edge, contains X and V. So two related concepts. One is the dual hypergraph. Here we switch it. It's the dual because we now flip the perspective. The nodes are the atoms, and the variables become the relations, also the edges, the hyper edges. So this is relevant for determining causality or resilience. And yet another perspective is the incidence matrix, which basically gives you both of these perspectives in one unified perspective, and that's needed, for example, to determine minimal query plans. So for the purpose of this tutorial, we only care about the hypergraph, where the nodes are the variables. So what is now a join tree? So a join tree is a tree. We take a query, and the nodes are formed by the atoms. And now we're going to have to place edges between those atoms, subject to an important property that's called the running intersection property, also called connected subgraph property. What is the idea? The idea is that if we have two tables that contain a variable, in this case W and P, W and S both contain P, then all of the nodes on the unique path between these two nodes, unique path because we are in a tree, there's no unique path, all of those nodes also need to contain that variable. And it turns out this can only be fulfilled by acyclic queries. An algorithm that's called G by overreduction allows us to find such a join tree given an acyclic query. So let's look at this algorithm. So we start with the query, we create the hypergraph, and now we want to find a join tree. So we want to find some tree between the nodes that we just here now created, represented by the atoms. The algorithm has two very simple steps. It's called an ear removal. And for an ear removal, we try to do two things. We want to remove isolated nodes. Isolated nodes are certain variables that are only contained in one single edge. So isolated means contained in one single edge. And we want to remove edges that are consumed by other edges. So in this case, if you look here at R, we see we can remove X from R. And once we have removed X from R, then the remaining variables, Y and Z, are completely contained in T. This is called that T consumes R. And what we normally keep track in the join tree is the variables that are shared between the atom that got consumed and the one that consumed, so the Y, Z. Another perspective that is not so common, but is actually quite helpful, is to also keep track of what are the variables that are removed, the isolated nodes. There's a different perspective that's very related, also to a variable elimination order, then comes up very often in different branches of computer science. Okay, so let's continue. Let's look at the edge W. Well, U is an isolated node, and once you have removed U, P and W are all contained in U. So we can now draw an edge between W and U. What about S? S has no isolated nodes, but it's completely contained in T. So we can also perform immediately an edge between those two atoms. And finally, we can say T has one isolated node, the rest gets consumed by U. And this here is now our join tree. The last one, a single one, can always be removed. So what is so special now about acyclic queries and join trees? So here is the idea. It turns out that with a particular sequencing of message passing, we can determine whether or not all of the tuples in a database perform in the query. So to illustrate this, let me first jump to an illustrating example to show what can go wrong. This here is the triangle query. R joins S on B, S joins T on C, and T joins R on A. Also drawn here. And also drawn is here a particular database instance. And now notice what happens here. This is very interesting. This tuple here, 0, 0, can join with a tuple from S, 0, 1. It could also join with a tuple from T, 0, 0. So this is something that we call it's locally consistent. If you just take any two tables and look at, is there any tuple that doesn't participate in the join, you would say no, there is no tuple. All of the tuples participate. But if you actually evaluate the query, you realize there is no single path that forms a triangle. So this, the triangle query on this particular database instance is empty. So it turns out the particular property of acyclic queries is that there is a local propagation message passing scheme that allows you that if all of the tuples are locally consistent, then you can conclude they are also globally consistent, and every tuple in the database will participate in some join. And the key idea of why trees allow this is the following idea. Whenever you have a tree, then this node here contains all of the information of the subtree rooted at that particular node. So you can actually create a message passing scheme bottom up from the leaves, this node to that node to this, and then this node to that node. This particular message that gets sent contains all of the information that is necessary and possible and relevant from the subtree rooted at that node. And a second conclusion we're going to see is that once we have then removed all of the tuples that don't participate in the joins, they're also called the dangling tuples, then when we just step by step join the tables, then every intermediate additional join can never decrease the size of the intermediate results. So let's go back to the example about the join tree and what doesn't work with cyclic queries. Here's our triangle query. If we try to create a join tree, we fail. Why? We can arrange all of the atoms, but if we then try to draw any two edges between them, we can never avoid that there is some path, in this case between T and R, that contains a table that doesn't contain all of the shared variables. X is contained in R, X is contained in T, but not an S in between. Interesting is, if you just add one more atom to the query, here W, X, Y, Z, this query is also called the beta triangle. The reason for why beta triangle is that the notion of acyclicity we use here is also called alpha acyclicity. There's another one that is called beta acyclicity, and for this is the minimal example for an cyclic query. The basic idea is that for a beta acyclic query, all of the subsets of the edges need to be alpha acyclic, and in this case we know if we just take R, S, and T, then we have a triangle. So for this one, the GYO reduction works. Why? Well, because R, X, and Y is completely contained in W, and so for S and T. So W consumes all of the other relations, and we can form a join tree. And the same with join reduction then works as follows. We first send messages up from R, S, T to W. We reduce W, and then we send it back down to the leaves. And then if we perform a join over the thus reduced relations, then we are guaranteed that all of the tuples that are in those tables participate in a join. Can still something go wrong? It can be. So if you just now, and we're gonna see this in a moment, if you just now take this query and perform a join, R1 with S1, with T1, with W3. This means if we perform the calculation in the following sequencing order, then actually we are toast. Why? Well, we have not obeyed the join tree. And what can go wrong for this? Let's look at this example. Here, if we perform a join between R and S first, then notice what happens. Both of those tuples join with both of those tuples. So the intermediate result size will be 4. But we know that the join ultimately only has output size 2. So how can we solve this problem? Well, if we still need also, doing the joins, we still need to follow the join tree that we have derived originally. So we perform joins R with W, then with S, and then with T. Then we're guaranteed that all intermediate result sizes are never bigger than 2. So I mentioned that semi-join reductions are quite powerful, and they pop up in all kinds of different areas one wouldn't expect. Here's an example from probabilistic databases. A couple of years ago, there was a very interesting paper from Alterno, Hung, and Koch. And the idea was here, they have observed that for safe probabilistic queries, safe plans can be quite inefficient at times. And the basic idea is that probabilistic databases and safe plans focus you to perform a certain sequence, joins in a certain sequence. And this sequence is sometimes not optimal. And they have come up with certain ideas to solve this problem. So it turns out you can get the same performance improvements, but just performing a deterministic semi-join reduction first. You first perform a deterministic semi-join reduction and then perform the join in normal sequencing steps, and you get the same performance improvements. So semi-join reductions can be extremely powerful in all kinds of different contexts, but whether or not they pay off, it depends on the concrete database instance, on the particular input. So Yannakakis is the algorithm that now allows us to evaluate acyclic queries on the join trees efficiently. And it has a very important property, namely, the complexity of the Yannakakis algorithm is O size of input plus output. And that's in a certain way the best you can do, because you need to at least read the input and you want to return all of the output. So you can't be faster than that. We'll later see you can still do better, but for that we need to change the perspective. But if you really want to have all of the output, then we cannot do better than this. And the idea of this Yannakakis algorithm is to first perform a complete semi-join reduction. We make 2 sweeps over the join tree, one bottom up, one top down, and then we make another pass over the join tree and put all the output tuples together. Let's look at a complete example, and we're gonna very quickly also repeat the GVO reduction. So we start from the hypergraph. We want to create a join tree. This means some tree between the tables. How do we perform it? Well, we see U can be consumed by T. We make an edge from U to T. Y is the variable that is shared. We see W has an isolated node. The rest gets absorbed or consumed by T. We see T and R. We can remove X. T gets absorbed by R. We could also make it the other way around. Here, it's not disconnected. S has only isolated nodes because it's disconnected. It's basically a Cartesian product in the join. And finally R. So here is our join tree. Now we look at the database, and now we use in 2 sweeps, we're gonna now reduce and remove all of the dangling tuples, those tuples that don't participate in any join. The first one is bottom up. Bottom up means we choose any reverse topological So we choose any reverse topological order. Reverse topological order means we always first visit all of the children before we visit the parent. So one example is 1, 2, 3, 4. And we perform the semi-tron reduction. So what is this? So U and T share one variable, Y. So we share all of the different values. We share them, we send all different values from U to T, in this case all of them, and then we observe, P4 can never participate in a join, so we can remove it. 2. In 2 we see X and Y are the shared variables. So we look just here at X and Y and look at all of the different pairs of X and Y. Now notice we don't need to send 4 values because these two, the last two, are identical. See, we only send 3 different pairs from A and B. To T, we see that 2 further cannot participate in any join. We go next. What about here? S and R don't share any variables. So we have, conceptually, we have to project S onto the empty set of columns. That's basically a Boolean query. And a Boolean query is true if there's at least one tuple. So the message we send here is the message true. This means, hey, there is at least one tuple. So nothing gets reduced from the left side in R. And from the right side, we have one more. So now we are finished. And by the end of the first sweep, the first bottom-up semi-tron propagation, the interesting thing that we now know is that this query needs to have at least one output tuple. Why? Because at the end, all of the information has been propagated to the root. So the root is now completely reduced. We have 2 tuples that survived the semi-tron reduction. So we know that both of those tuples will participate in at least one output tuple. So next, we make a pass top-down. Now we do it in some topological order. Topological order means we can only visit a child if we have visited its parents first. Its parents, its unique parent. So here's one example, 1, 2, 3, 4. So we send messages. With the same situation, R sends the message true because we have no shared variable. Nothing gets reduced from R. Next, we send from R these 2 values. Nothing gets reduced. Here we only have now B1 and B2. Notice that this information was originally propagated from W to T. Now in this pass, it gets further propagated to U. And the last one, so W. So at the end of both passes, all of the tuples that survived this semi-tron reduction will participate in at least one join. So now comes the second phase. The second phase is the join phase. So now we perform one more top-down evaluation from the root to all, also one join, again in topological order. We first visit the parent before we visit its children, and we stitch together the tuples one table at a time. So we start with all of the tuples from R. We join them with all of the tuples from S. They don't share any variables, so it's the Cartesian product. So we're gonna add 2 columns and we make it 3 times as big. We then go to table T. This gives us one more column P. We don't get more tuples. We go to 4 next. 4 doesn't add any additional variable. We already have Y, so it cannot increase in size. It stays the same size. And the last is then we add the column U, and this is here our output. So notice the following: in just ON, in the size of the database, we were able to determine whether or not the query has at least a join. This means whether the Boolean query is true or false. And then for computing all of the results, we need to make one more pass down. In the worst case, this takes exactly R. This means the time it takes us to, R is the size of the output. So indeed, it's O input plus output. So can we do better? And on a certain perspective, we can't do better than O input plus output. But in another perspective, we can. So what is this perspective? So let's look again what happens in the Yannakakis algorithm. In the first step, we reduce the database. This takes ON input, and then we create all of the tuples and then dump these tuples as output to the user. So the total time it takes us is ON plus R. At this time, we dump all of the output tuples R. The time it takes, the number of tuples we get. How could we be better? This is something that also has been quite popular in the last couple of years in our community. We could think about an enumeration framework. What means enumeration framework? Well, the idea is that after we have performed the reduction, we may not have to wait OR to return the first tuple. We could immediately start returning some tuples and more and more and more. And an ideal way that in this to happen is that in the time O n, we can get the first output, something also called time to first. Then we have time to k as we output tuples, and then time to last is, well, the time until we get the last tuple. Asymptotically, this should not be worse than our Yannakakis framework. So let's look how this works in practice. So what is the power of this is that here's an example. It would take us around 10 seconds to get all of the output tuples. But if we change perspective, we get in about a 50th of the time the first tuple, and then we get more and more and more and more. And because of some overhead, this may take more time. Now, when is this extremely powerful, this perspective? If we have some order, if you want to get the first results, it's the most important ones, very early, and don't want to get all of the results. So this is the change of perspective. Intuitively, you can think about the Yannakakis algorithm being an algorithm that visits each table one after the other. So it's a table at a time algorithm. As enumeration says tuple at a time. We go depth first in the join tree, try to get a tuple, the next tuple, and the next tuple. And this may have some overhead, so it may take more time to last, but it really gives us the first results far earlier. So what do we have to change in the Yannakakis algorithm to get this enumeration? So here is what we're gonna do. We still perform a semi-join reduction, but then we change the join phase. And the intuition is, what we just discussed, we don't visit each table at a time, but we think about tuple at a time. So let's look at how we can do this. So we start with the first tuple in the first table, and then we just visit, again, each table and look for any tuple that is consistent with our original tuple. And this can be done efficiently with the right indexing structure and with the right sorting of the tuples in the tables. So we have now returned after the semi-join reduction and one pass through the tree, the first tuple. Next, we see, can we just change here? What is the next tuple that's consistent with the other tuples? Well, here it turns out there is nothing that's consistent with the same xy, a1, b1, neither in u, neither in t, but as it is, we can move to the next tuple, and we can return the next output tuple. And we can repeat this. And now we go back to the first table. We choose here the next output tuple, and again, update and make a pass over the tables and find the next set of tuples that are consistent with that tuple. And then we repeat this. We see, can we go here to the next one? But here we can, A1, B2, A1, B2, and we have the next tuple. Now we need to go back to table S, all the way to S, make the next, and repeat this, and now we're done. So this is the power of the change of perspective, that in the Yannakakis, we visit table at a time, and therefore we get all of the tuples at once. The other one, we jump between the tables. We get time to first, we get the first tuple very early, but therefore there may be some overhead to get the last tuple. So last part here is what changes with protractions. So we get similar to slightly modified guarantees. Concretely, for Yannakakis, we are guaranteed for arbitrary protractions to get all of the results in n plus n times r. This means input times output time. Notice it's usually just written as input times output, but this assumes that the output is always at least size 1. Or if you have no output, then the return is like false. I think this is the more correct way to write it. This means if the output is 0, you still get a linear guarantee to get the result that there is no result. It turns out for enumeration, this works in general with linear delay and also leads to a time to last of the same time guarantee. So both Yannakakis and enumeration actually will give you the result, the last result, at the same guarantee. If the protraction fulfills certain criteria, also called free-connex, then we're actually getting back the original guarantee for the Yannakakis for the full conjunctive queries. And the same also with enumeration, which is done with constant delay. We get also the last result in input plus output. So notice the change. In general, we get here a linear delay between the individual answers, and this leads to a linear overhead until the last result. So what is free-connex? So free-connex is the idea that you take an acyclic query and then you add an edge for the set of projected variables, and the remaining query is still acyclic. So let's look at this in an example. Assume you have a conjunctive query T, X, Y, Z, W, Y, Z, U. And you want to project either on the variables X, Y, or X and U. In the left case, the additional edge X and Y can be consumed by the previous edge T. Therefore, G/O still works, and it is acyclic. On the right side, this is not the case. This query here, this hypergraph, is cyclic, and therefore this query is not free-connex. So let's illustrate what kind of goes wrong. So to say, with a query that is not free-connex, we have here a chain query, RXY, SYZ, TZU, but then we project on the endpoints. So notice now this query is not free-connex because now we have here a cycle. So in the join phase, the way we could solve this query is we join R with S. We can't project anything away because we need the Y variable for the join, and the X, it's part of the output. Afterwards, we can project Y away. And after we join the last table, we also project Z away to get Q. Here, an example database. If we first join R with S, we get an intermediate result size of quadratic size of the input, n to the power of 2, while the output is only linear. And this explains this linear overhead. Output size is linear. Join phase takes input times output. Output is n. Therefore, the total time is n to the power of 2. So a linear overhead. So let's summarize here. What you've seen, acyclic queries imply a join tree and can be found with the G/O algorithm. Semi-join reductions work on trees and can be extremely powerful to speed up inference and query evaluation. Yannakakis works on such acyclic queries. It's basically a semi-join reduction followed by a join phase, and it gives an optimal time guarantee of input plus output for full conjunctive queries. For channel projections, we have here linear overhead. And enumeration slightly modifies Yannakakis, but somehow it's still of the same flavor. And this modification allows you to start with enumerating, returning results earlier. And intuitively, it's basically a depth first instead of a breadth first exploration of the join tree.